Welcome to this explainer. If you're a materials engineer tasked with keeping critical, high-temperature, high-pressure infrastructure from, well, catastrophically failing, you are exactly where you need to be. Selecting the right material is an exacting science. So today, we're diving deep into a true industry heavyweight, ASTM A23.
Let's run through our agenda real quick. We'll kick things off by defining ASTM A213. Then we'll profile the T22 grade, dive into heat treatment intolerances, compare A2013 with A335, and finally wrap up with quality control and traceability.
Because, honestly, it all comes down to one massive engineering puzzle. How exactly do you contain extreme pressure and heat in boiler superheaters and heat exchangers without the whole system failing? Beating high-temperature corrosion and immense internal pressure means you absolutely have to know your materials inside and out.
All right, Part 1. Defining ASTM A213. Let's start from 30,000 feet. ASTM A213 is the go-to standard specification for seamless ferritic and alloy steel tubes, and we're specifically talking about boilers, superheaters, and heat exchangers here. We're not running water through an office building, right? This is the strict manufacturing playbook for low-alloy piping built for intense heat transfer. It even covers wall thicknesses from a razor-thin 0.015 inches all the way up to half an inch.
Now, you might be wondering about the difference between ASTM A213 and ASME SA213 because people swap these terms all the time, but they actually do two totally different things. ASTM A213 is your global how-to manufacturing guide. It's the recipe. ASME SA213, on the other hand, is the legal adoption of those rules. If you're bound by contract or local law to build a safe pressure vessel, ASME SA213 is the code you're actually answering to.
Okay, moving to Part 2, the T22 grade profile.
Let's look at a real-world case study, the SA213 T22 grade. The physical stamps on those seamless steel tubes sitting on the factory floor tell a story. T22 is a 2.25% chromium, 1% molybdenum ferritic alloy steel. When the heat gets turned up and you absolutely cannot afford warping or corrosion, this is your workhorse. But what makes it tick?
It's all in the chemistry. The real magic happens with that chromium and molybdenum combination. The chromium, sitting right between 1.9 and 2.6%, is what gives you that incredible oxidation and corrosion resistance. Then you have the molybdenum at roughly 1%, which is the secret sauce for high temperature strength and fighting off creep. Toss in strictly controlled amounts of carbon, manganese, and silicon for weldability, and you've got a powerhouse material.
But hey, it's not just about what you put into the mix, it is entirely about what you keep out. Phosphorus and sulfur are capped at a maximum of just 0.025% each. That's a tiny number, but it's an absolutely crucial safeguard. If those elements creep up, your steel becomes brittle, and your structural integrity under load goes right out the window.
Right, on to Section 3, heat treatment and tolerances.
So you've got the chemistry perfectly dialed in, but how we actually treat the metal physically is what locks in its stability. For T22, the gold standard is normalizing followed by tempering. Step 1, you normalize it by heating it up to around 900 to 950 degrees Celsius to completely homogenize that internal grain structure. But it's way too brittle at this point. So Step 2, you temper it between 700 and 750 degrees Celsius. That balances out the toughness, relieves the internal stress, and leaves you with a beautifully stable, tempered bainite structure.
And that specific heat treatment translates into some rock-solid guarantees. You're looking at a minimum tensile strength of 60,000 psi and a yield strength of 30,000 psi. Plus, the hardness is strictly capped at a maximum of 163 Bernal. That cap is super important because it ensures the tube stays tough enough so it won't just crack or fail after years of heavy service loads.
Of course, strength means nothing without precision. The outside diameter and wall thickness tolerances are incredibly exacting. For cold-drawn and cold-rolled tubes, we're talking tolerances down to fractions of a millimeter. But take the hot-rolled specs, for instance. There is literally zero negative tolerance allowed for the wall thickness. It can be up to 28% thicker than you specified, but it can never, ever be thinner. That guarantees your pressure containment is never ruined by a random thin spot.
Let's jump to Section 4, comparing A213 and A335.
As a materials engineer, knowing what to specify often means knowing exactly what not to use. You'll see A213 and A335 compared constantly since they both handle high heat. But here's the catch.
A335 is built primarily as a pipe for high-temperature transport. It has some corrosion resistance, sure, but not nearly enough for the truly nasty environments. A213, on the other hand, is engineered specifically as tubing that thrives in highly corrosive heat exchange setups. If extreme corrosion is on the table, A213 wins hands down, every time.
Finally, Section 5, Quality Control and Traceability.
Before a single piece of this material leaves the factory floor, it has to pass a rigorous checklist. ASTM A1016 mandates some very strict marking requirements so we have absolute traceability from day one. Every single bundle has to loudly and clearly display the standard, the steel grade, exact dimensions, heat and batch numbers, and whether it was hot or cold finished.
When you see those precise markings physically stamped on the bundle in the field, you know it's not just administrative red tape. That's your proof. It verifies that the metal in front of you is exactly what you ordered and that it survived the intense testing protocols tied specifically to that exact heat and batch number.
And it really is a gauntlet of tests. Both A213 and A335 go through rigorous chemical analysis to verify that exact alloying mix we talked about. Then comes destructive mechanical testing for tensile and yield strength, followed by crucial non-destructive testing like ultrasonic and radiographic scans to look for hidden internal flaws. Toss in a strict visual inspection for surface defects, and that's how conformity is guaranteed before it ever hits your loading dock.
So we've seen how meticulously ASTM A213 controls the chemistry, the heat treatment, and the testing to squeeze every last drop of performance out of alloy steel. But it does leave us with a fascinating question to chew on. As our industrial environments get even hotter and the pressures get even more intense, how far can we actually push the limits of our current alloy steel standards before we have to invent entirely new exotic composite materials? It's a massive challenge for the future of material science. Thanks for joining me for this explainer.